All right, let's get into it. Today, we're going to crack a full 10-mark AQA GCSE Physics question. Now, 10 marks, that is a massive chunk of your final grade, so it's worth knowing how to lock them down. We're going to break down every single part, the math, the theory, the graph, so you can feel confident you're grabbing every point.
Okay, so take a look at this. It all kicks off with a pretty standard diagram of a mains lighting circuit. You've got your lamp, a switch, and of course the live and neutral wires. Looks simple, right? Well, this little setup is the foundation for all three parts of question 9.
So, first up is question 9.1. This is the big one, a 5-mark calculation. The whole scenario is about a faulty circuit giving someone a bit of an electric shock, and our job is to figure out that person's electrical resistance. Right, so what have we got to work with? The question tells us the power being transferred is 5.75 watts, and the potential difference is 230 volts, which, is the standard voltage for UK mains power. With just those two numbers, we need to find the resistance.
Now, you might be thinking, how do I get resistance from power and voltage? Well, you can't, not directly anyway. It's a two-step process. First, we've got to find the current. We use the power equation, P equals I times V, pop in our numbers, and rearrange it. That gives us 5.75 divided by 230, which works out to a current of 0.025 amps.
Okay, so we've got the current, now what? Well, now we bring in the classic, the one and only Ohm's law, V equals I times R. We just need to shuffle it around to get resistance on its own. So R equals V divided by I. We plug in our numbers, 230 volts divided by the 0.025 amps we just found.
And boom, that gives us our final answer, 9,200 ohms. And just a tip, for a chunky 5-mark question like this, you have to show your work. Laying out every step clearly is just as crucial as getting that final number right.
All right, that was the math part. Let's switch gears to the theory side of things with question 09.2. This is a 3-mark explainer, and it's all about the real-world safety stuff an electrician has to know.
The question really gets to the core of electrical safety. I mean, why is it so important to disconnect the mains? We all know it's a rule, but this is about the physics of why that shock happens in the first place.
So how do you nail this for all 3 marks? It's all about one key idea, potential difference. The best way to think about it is like a waterfall. You need a difference in height for water to flow, right? Well, for electricity, you need a potential difference. The mark scheme is super clear. You have to say the live wire is at a high potential, 230 volts. The electrician, standing on the ground, is earthed, meaning they're at 0 potential, 0 volts. So when they touch that live wire, they basically become a bridge between the high point and the low point. That huge difference in potential forces a current to flow right through them. That's the shock.
And now for the final piece of the puzzle, question 09.3. This is just for 2 marks, but it's a bit different. It's all about reading a graph that connects the frequency of electricity to something called the let-go current.
Okay, here's the graph from the exam paper. Let's break it down so it's not so intimidating. Along the bottom, the x-axis, you've got frequency in hertz. And up the side, the y-axis, that's the let-go current. What does that mean? It's the maximum current a person can handle and still be able to physically let go of the wire. And you higher, and their muscles just lock up. So, with that graph in mind, here's the question they throw at us. We know the UK mains frequency is 50 hertz. So using the graph, explain why it would actually be safer if the frequency was something else. You don't need any complex calculations here. The answer is literally staring you in the face on this graph. Just look at the curve. Where is the lowest point? It bottoms out right at 50 hertz. That means the let-go current is at its absolute minimum at that frequency. So, weirdly enough, the frequency we use in the UK is actually the most dangerous one, according to this data. At any other frequency, higher or lower, a person could take a larger current before their muscles seize up, which technically makes it safer.
So let's just step back and look at what we've covered. This one 10-mark question really put us through our paces, didn't it? It tested our skill with Ohm's law and the power equation, it checked our understanding of fundamental safety with potential difference, and it even made us analyze data on how AC frequency affects the human body.
And that's how you break down a beast of a 10-mark physics problem. But it gets you thinking, doesn't it? We've just focused on one simple circuit, but these principles, earthing, potential difference, safety cutoffs, they're in practically every single thing you plug into the wall. So, what other devices you use every day are secretly using this exact same physics to keep you safe? Something to think about. Thanks for joining me.